This solar panel is rated at 400 watts. I mounted it on my roof, south-facing, 30-degree tilt. December. Average output over 30 days, 112 watts. That is 28% of the rated number, and that was on clear days. On overcast days, which December produces more of than June, the number dropped to 60, 50, sometimes 40 watts. From a 400-watt panel. The spec sheet number and the real number are not the same number. Today I am going to show you exactly how far apart they are for 5 different power sources, with the math that actually matters for a 72-hour outage. I want to be clear about what this episode is and what it is not. This is not a takedown of solar energy. Solar is one of the most important technologies on the grid and in personal resilience planning. This is not an argument against batteries or generators. This is a calibration exercise. The gap between the number on the packaging and the number in your log is not a flaw in any one product. It is a systematic problem with how specifications are communicated to consumers. You are told the peak performance number under ideal conditions, and you are expected to extrapolate your real-world plan from that. The problem is that a bad plan based on a wrong number is worse than no plan. If you believe you have a 400-watt power source and you plan your 72-hour outage around 400 watts, you will run out of power at the 12-hour mark and have no backup because you believed you had covered it. That false confidence is the actual danger, not the technology, the false confidence the specification creates. Last episode, we looked at what Texas showed us, a grid that failed at scale and the cascading dependencies that turned a power outage into a water crisis and a heating crisis simultaneously. The conclusion was straightforward. You need a power source that does not depend on the same infrastructure that just failed. This episode is about testing those alternative sources, not reading their packaging, testing them. There is a difference. The packaging is written by a marketing department. The test results are written by physics. Before I get into the individual sources, I want to address the question I get most often from people who have already bought solar. Is my installation doing what it should? The answer requires a baseline. Most residential inverters have monitoring software that logs daily production. If yours does, go look at December. Take your lowest 7-day average. That is your winter floor. If your monitoring shows you regularly above 80% of your system's calculated December output, good. Your system is performing. If you are consistently below 60% and you have no obvious shading, something may be wrong. Inverter clipping, panel degradation, shading from a tree that has grown since installation, soiling from dust or debris. Panel degradation is real. Most panels lose 0.5% to 1% of rated capacity per year. A 10-year-old system with average degradation is running at 90 to 95% of its original output. Not dramatic, but measurable. Factor it in. Your 12-year-old panels are not the panels on the spec sheet anymore. Let me start with how solar panel ratings work, because this is the foundation of everything. A panel rated at 400 watts will produce 400 watts under one specific set of conditions. 1,000 watts of solar irradiance per square meter, cell temperature of 25 degrees Celsius, and a standard air mass coefficient of 1.5. This is called STC, Standard Test Conditions. It is a laboratory benchmark. It does not describe your roof in December. It does not describe your roof in June either. Most real-world installations run at 70 to 80% of STC, even in summer. In winter, at higher latitudes, you lose irradiance because the sun is lower on the horizon. You lose efficiency because the calculation assumes 25 degrees. December air helps cells run cooler, which actually improves efficiency slightly, but the irradiance loss dominates. The result is the number I logged, 28% of rated output on a clear December day. The irradiance number is worth dwelling on because it is less intuitive than temperature. Solar irradiance, the power density of sunlight hitting a surface, varies dramatically by season and angle. At the equator, at solar noon in summer, you can approach that ideal 1000 watts per square meter on a surface perpendicular to the sun. At 40 degrees latitude in December, the sun reaches a maximum elevation angle of roughly 26 degrees above the horizon. That shallow angle means the sunlight travels through more atmosphere, scattering and absorbing more energy before it reaches your panel. Even on a perfectly clear December day, peak irradiance at that latitude is somewhere around 400 to 500 watts per square meter, 40 to 50% of the STC benchmark before you account for anything else. Add cloud cover, particulate haze, and the fact that peak irradiance lasts only an hour or two around solar noon, while the rest of your daylight hours produce less, and the average irradiance across your usable daylight hours drops further. The panel is not broken. Physics is working exactly as expected. The spec sheet just does not tell you what happens when the physics are seasonal. There is a better metric than STC, PVGIS, the Photovoltaic Geographical Information System, maintained by the European Commission's Joint Research Centre. It uses real irradiance data by location and month to calculate realistic energy production estimates. I ran my installation through it. The December prediction matched my measured output within 8%, far closer to reality than the STC spec sheet number. If you are planning a solar installation or evaluating an existing one, run your address and panel specs through PVGIS before making any capacity assumptions. The tool is free, the data is real, and it will tell you your December number before December arrives. Here is why that matters for your planning. A 400-watt panel in the marketing brochure suggests you can run a 400-watt device continuously. In December reality, you have a 112-watt source averaged across the daylight hours you actually get, which in December at 40 degrees latitude is about 8.5 hours. That means your daily energy budget from one 400-watt panel in December is approximately 950 watt-hours. Call it 1 kilowatt-hour per day. The average American household uses around 30 kilowatt-hours per day. One panel at rated output, 1 kilowatt-hour. That is 3% of average household consumption, not a backup. A footnote. Now, a single panel is not a full solar installation. A real residential system runs 8 to 20 panels. But the math still matters, because the same ratio applies to every panel in the array. Whatever you paid for, whatever the spec sheet promises, multiply by 28% in December. That is your winter number. Not your peak summer noon number, your winter number. The one that matters when the grid fails during the ice storm that the grid is most likely to fail during. I tested 5 energy sources over the 30-day period: solar, portable power station, gas generator, propane system, and hand crank generator. For each one I tracked 3 numbers: rated output from the manufacturer, real measured output under test conditions, and cost per real kilowatt-hour, including fuel, maintenance, and amortized hardware cost over 5 years. That last number is the one almost nobody calculates, and it changes every verdict. Source 2, portable power station. I tested a 1 kilowatt-hour unit, rated capacity 1000 watt-hours. Usable capacity at 20 degrees Celsius ambient temperature, 840 watt-hours. Battery chemistry loses capacity in cold. The lithium cells in this unit are rated for their full capacity at room temperature. Drop to near freezing and you lose 15 to 20%. If you store this device in an unheated garage in winter, you might open it during an outage and find 60% of expected capacity. Store it inside. That is not a tip, that is a system requirement that should be on the packaging and is not. The 840 watt-hour real capacity means phone charging for several days, LED lighting for a couple of nights, a small fan or radio continuously. It does not run a refrigerator for more than a few hours. It does not run a furnace blower at all. For communications and lighting in a short outage, useful. For powering your home's critical systems across 72 hours, insufficient as a standalone source. I want to pause on the furnace blower point because it is the most common miscalculation I see in preparedness planning. People buy a portable power station, check that it has an AC outlet, and assume it will run their furnace. The furnace itself may burn gas, but the blower motor that circulates the heated air through your ductwork is electric. A standard residential furnace blower draws between 300 and 800 watts, depending on the motor size. That means at moderate draw, call it 500 watts, your 1 kilowatt-hour power station runs the furnace blower for roughly 90 minutes before it is at 50% capacity, 6 hours before it is empty. A December night is 12 hours. The math does not close. This is not a failure of the power station, it is a failure of planning based on the spec sheet rather than the actual load calculation. I will cover this in depth next episode on thermal layer, but the preview is this. If heat is your primary concern in a winter outage, you need a direct heating source that does not depend on electrical distribution. The power station is not that source. Cost per real kilowatt-hour for the power station. This unit costs around $300, has a rated cycle life of 500 to 1,000 cycles before dropping to 80% capacity. If you cycle it once per week, which is aggressive for emergency use, it lasts roughly 10 to 20 years. Amortized cost per cycle, 30 to 60 cents per kilowatt-hour of usable energy, before accounting for electricity to recharge it, which adds another 10 to 15 cents depending on your grid rate. Total, 45 to 75 cents per real kilowatt-hour. That is expensive compared to grid power at 12 cents average. But grid power is unavailable during the outage you are planning for, so the comparison is not grid power versus portable station, it is portable station versus darkness. Source 3. Gas generator. I tested a 2,000-watt portable generator running on regular gasoline. Rated output, 2,000 watts. Real continuous output at rated load, 1,800 watts, 90% of spec, which is actually respectable. Gas generators are more honest about their numbers than solar panels because internal combustion is less sensitive to ambient conditions. The real story with generators is not the watt number, it is the fuel math. This generator consumes approximately 0.6 gallons of gasoline per hour at 50% load. A 72-hour outage at moderate use, not running everything, running the essentials, requires roughly 30 to 40 gallons of fuel. The average car holds 12 to 15 gallons. You need 3 full tanks of fuel, stored and stable, before the outage to run a generator through 72 hours. Gasoline degrades. Untreated fuel stored for 6 months loses octane and starts gumming carburetors. You need fuel stabilizer, rotation schedule, and a storage system that complies with fire codes. The generator is not a device, it is a fuel logistics operation. And I want to be direct about the safety requirement that gets skipped in most generator content. You cannot run a gas generator indoors. Not in the garage with the door open. Not in the basement. Not in an enclosed porch. Carbon monoxide is odorless, colorless, and lethal. The CDC reports that each year, roughly 400 Americans die from unintentional carbon monoxide poisoning, not related to fires. And generator use during power outages is a leading cause. During the 2021 Texas outage, there were at least 17 reported carbon monoxide deaths from indoor generator use in the first week alone. The generator must be outside, a minimum of 20 feet from any door, window, or vent opening. In December, in the ice storm. This is a real operational constraint. If your plan requires someone to go outside to manage fuel and check a running generator in a winter storm, factor that into your comfort level with the plan. The other constraint nobody talks about: noise. A 2,000-watt generator at full load produces roughly 65 to 75 decibels at 20 feet. That is lawnmower level. In a residential neighborhood during an outage, particularly a neighborhood-wide outage where people are already stressed and cold, a continuously running generator is an advertisement. I am not making a security argument here. I am making a community cohesion argument. Your neighbors can hear it. If some of them need help and you have power, that is a decision you will have to make. Plan for the social dimension, not just the technical one. Cost per real kilowatt-hour on the gas generator. Hardware amortized over 10 years plus fuel at current prices puts this at approximately 40 to 60 cents per kilowatt-hour, depending on load efficiency. Similar to the power station, but with a critical difference: the generator scales. One power station gives you 1 kilowatt-hour total. The generator gives you unlimited kilowatt-hours as long as you have fuel. For extended outages beyond 48 hours, the generator wins on capacity. For short outages or situations where fuel access is cut, ice storm, flood, supply disruption, the generator is a liability that weighs 70 pounds and requires outdoor operation in the storm you are trying to survive. Source 4. Propane. I tested a 1-pound canister system and extrapolated to larger tanks. Propane has real advantages over gasoline. It stores indefinitely without degrading, it burns cleanly, and a standard 20-pound barbecue tank holds roughly 43,000 BTU of energy. Converted to electrical equivalent, about 12.5 kilowatt-hours if you are using it for a propane generator. Propane generators are less common and more expensive than gasoline equivalents, but the fuel logistics are cleaner. For heating applications, which is where propane genuinely excels, the economics shift dramatically. We will cover thermal layer in the next episode in detail, but the summary is this: propane used directly for heat is roughly 3 times more efficient than propane converted to electricity to run an electric heater. If heat is your primary need, do not convert propane to electricity and then back to heat. Burn it directly. There is one propane constraint that matters enormously in cold weather: pressure drop. Propane vaporizes inside the tank to create the gas pressure that feeds your appliance. At very cold temperatures, below -44 degrees Fahrenheit, which is propane's boiling point, the liquid inside the tank cannot vaporize and the pressure drops to 0. Your appliance stops. This is not a common scenario in most of the continental United States, but it is relevant in northern climates and relevant to understand when placing tanks. A tank sitting in a snowdrift at -20 will produce lower pressure than the same tank at 40 degrees. For dual-stage regulators and properly sized tanks, this is manageable. For small 1-pound canisters in extreme cold, it can mean a camp stove that works at 40 degrees and fails at 0. Test your equipment at the temperatures you expect to encounter. Not in your living room in September, outside in January. Cost per real kilowatt-hour for propane electrical generation: approximately 80 to 100 cents per kilowatt-hour at current propane prices. More expensive than gasoline generation. The value proposition for propane is not cost efficiency, it is logistics. Unlimited shelf life, no degradation, widely available in large quantities before a storm, and dual use for cooking and heating without conversion losses. A 20-pound tank at $4 per gallon equivalent costs around $16 and delivers roughly 12 kilowatt-hours of electrical equivalent, or 4 to 5 hours of direct heating for a room. The math changes considerably when you are buying a 200-pound tank with bulk delivery pricing. At that scale, propane becomes competitive. At the £1 canister scale, it is emergency communications money, not heating money. Source 5. Hand crank generator. I tested a small emergency unit rated at 10 watts. Real sustained output from a reasonably fit adult, 5 to 7 watts over 10 minutes before fatigue. That is not a power source for anything except charging a phone from 0 to 15% in about an hour of steady cranking. Do not plan your household power around human effort. A person can sustain roughly 100 watts of mechanical power output for short periods. Elite cyclists do this, not average adults during a stressful winter outage. The hand crank generator is a last resort communications tool. It belongs in a kit, not in a plan. I want to be specific about where the hand crank has genuine value. Powering a small emergency radio receiver. A weather radio or NOAA receiver draws around 3 to 5 watts. The hand crank can sustain that. Meaning, during an outage where every other power source has been exhausted, you can still receive emergency broadcast information as long as someone can turn the crank. That is a narrow but real use case. Emergency broadcasts have saved lives. Knowing when conditions are safe to go outside, when the outage is expected to end, when roads are passable, that information has value. The hand crank gets you access to it for as long as you can crank, nothing more. Build your kit around that specification, not the 10-watt marketing number. Here is the comparison table. 5 sources, 3 numbers each. I am going to go through this carefully because this is the data that matters for actual planning decisions. Solar, 400-watt panel. Spec 400 watts, real 112 watts in December. Cost per real kilowatt-hour, approximately 25 cents over a 20-year system lifespan, including installation. The lowest long-term cost of any source, but only if you have the capital for installation, own your roof, and have planned your system around real winter output, not spec sheet output. The critical constraint: solar produces nothing at night and very little on overcast days. A December outage that starts at 3 in the afternoon means you have 0 solar production for the next 16 hours. The panel rating is irrelevant. You need storage to bridge the gap, which means pairing solar with a battery bank. And that battery bank has its own cold weather capacity loss, as described for the portable power station. A solar plus storage system designed for real December performance is a serious investment, not an afternoon project. Portable power station, 1 kilowatt-hour unit. Spec 1000 watt-hours, real 840 watt-hours at cold temperature. Cost per real kilowatt-hour, 50 to 75 cents. Best use: short outages under 24 hours. Communications, lighting, device charging. Worst use: running high-draw appliances, refrigerator, furnace blower, electric heater. The power station's real value is in its simplicity and indoor operation. No fuel, no exhaust, no noise. You can run it next to your sleeping family in the living room. That operational simplicity is worth the cost premium per kilowatt-hour in many scenarios. Gas generator, 2 kilowatt. Spec 2000 watts, real 1800 watts continuous. Cost per real kilowatt-hour, 40 to 60 cents plus fuel logistics. Best use: extended outages with fuel pre-stored, covering high-draw loads like refrigeration and furnace blower in rotation. Worst use: situations where fuel supply is disrupted, outdoor operation is dangerous, or noise and exhaust are operational constraints. The generator is the highest capacity portable option by a significant margin. Nothing else in the consumer market gives you continuous high power output for the price. The trade-offs are real, but for a household committed to managing them, the generator covers scenarios the other sources cannot. Propane system. Spec varies by unit. Real output, similar efficiency to gas for electrical generation. Cost per real kilowatt-hour, 80 to 100 cents for electricity generation, far lower for direct heat. Best use, cooking and direct space heating, independent of electrical infrastructure. Long-term fuel storage without degradation. Worst use, primary electrical source on cost grounds when gasoline generation is available. The propane system shines when you reframe it as a thermal source rather than an electrical source. The decision to buy propane heating equipment versus electrical backup is not one decision. It is a layer decision. Propane handles thermal layer. Gasoline or solar handles electrical layer. They are not competing for the same role. Hand crank. Spec 10 watts. Real 5 to 7 watts sustained. Cost per real kilowatt-hour is not a meaningful metric for this source. It belongs in emergency communications planning. Not energy budgeting. Not a power source. A last resort communications tool with a specific, narrow, genuine use case. The verdict column for a 72-hour outage covering one normal household's critical loads: refrigeration, furnace blower, communications, lighting, phone charging. Solar alone in December fails to cover the load without large battery storage. Power station alone fails to cover 72 hours at household draw rates. Gas generator covers it if you have fuel stored and the operational constraints are manageable. Propane covers direct heating better than anything else in the lineup. The working answer for most people is a layered combination. Portable power station for the first 12 to 24 hours, covering communications and lighting. Gas generator for extended coverage of high-draw systems if the outage extends past day 1. And direct propane for heat independent of any electrical generation. The combination is not expensive. The power station is $300. A small generator with one season of stored fuel is $800 to $1,000. A propane setup, 20-pound tank, camp-style 2-burner stove, and a small propane space heater is under $300. Total system cost, $1,500 to $1,600. For comparison, the median insurance deductible for a frozen pipe claim in Texas after the 2021 event was $2,000. Before coverage limits, you are not spending money on preparedness. You are spending money on a cheaper outcome. One more number that does not appear on any spec sheet: the cost of inaction. Last February in Texas, the average household that lost heat for 72 hours spent between $1,000 and $3,000 in property damage from burst pipes alone, not counting hotel costs, food loss, or the medical costs from hypothermia-related events in vulnerable populations. A portable power station costs $300. A gas generator with a season of fuel costs around $800. The insurance math is not complicated. You are not buying a luxury. You are buying a cheaper outcome than the one the alternative produces. Let me say that differently because I want it to land. Most people think of preparedness spending as a discretionary cost, something you do if you have extra money and extra worry. The framing is wrong. It is not a discretionary cost. It is a risk premium. Insurance companies price outage risk. They do not recommend a 72-hour kit. They charge you more to rebuild your house after the pipes freeze because you did not have heat for 3 days. The risk is already priced into your life. You are already paying for it. The question is whether you pay the insurance company after the event or pay the hardware store before it. Before is cheaper. This is arithmetic, not philosophy. I also want to address the objection I anticipate. But I rent. I cannot install solar or a generator. Correct on solar, not correct on everything. A portable power station requires no installation. A propane camp stove requires no installation. A 20-pound propane tank requires no installation. An LED lantern and a battery-powered weather radio require no installation. There is a version of this energy layer that fits in a closet, costs under $500 total, and works for any living situation, including a studio apartment. It does not cover everything. It covers the most critical things: communications, lighting, minimal cooking, and information access during an outage. That is the floor. Build to the floor first. Then build up from it as your situation allows. The spec sheet says X. Reality says Y. The distance between those two numbers is not a defect in the product. It is information. Verified, tested, logged information. Use it. Let me give you the load calculation framework I use, because this is what makes planning real rather than theoretical. Start by listing every electrical load you need to maintain during an outage. Do not list everything in your house. List what you need to maintain for 72 hours to keep your household safe and functional. Refrigerator: 100 to 400 watts running, 1500 watts startup surge. Furnace blower: 300 to 800 watts. Basic LED lighting, 3 rooms, 30 to 60 watts. Phone charging, 2 phones, 20 to 30 watts. Medical devices, if applicable, varies widely. The sum of your critical loads, not peak simultaneously, but staggered rotation, defines your minimum power requirement. For a typical household without medical equipment, this number is often somewhere between 300 and 800 watts, average draw across the outage, with periodic surges for compressor startups. Now match that requirement against your sources. 800 watts average draw for 72 hours is 58 kilowatt-hours total. Your 1 kilowatt-hour power station covers less than 2% of that requirement. Your gas generator covers it, but burns approximately 35 gallons of fuel. Your solar array in December, 4 panels, 1600 watts rated, approximately 450 watts real average, produces roughly 3 kilowatt-hours per day across 8.5 daylight hours. Over 3 days, 9 kilowatt-hours. 9 versus 58. Solar closes the gap, but does not eliminate it in a December scenario without substantial battery storage. The layered system is not a preference, it is the arithmetic. There is one category of load that changes the calculation significantly: medical devices. A CPAP machine draws 25 to 80 watts, depending on the unit and whether it has a heated humidifier. If someone in your household uses one, that device is not optional. An oxygen concentrator draws 150 to 600 watts and runs continuously. An insulin refrigerator draws 30 to 60 watts. These loads are small compared to furnace or refrigerator, but they are non-negotiable. If your household includes anyone dependent on powered medical equipment, that equipment defines your minimum viable power system, not comfort, survival. If you do not know the wattage of every medical device in your home, check tonight. The number is on a label on the device or in the manual. Write it down. It goes on your load calculation sheet. The number I want you to remember from this episode is not 400 watts. It is 112. That is the December number. That is the number that matters when the grid fails during the storm that causes grids to fail. Build your plan around the real number, not the spec sheet number. Every other decision in your energy layer follows from that one correction. I have been running this audit for 3 years. The single most consistent finding across every layer, power, water, food, heat, communications, is the same. The plan that feels complete because the spec sheet says it covers the need is the plan that fails first. Not because the hardware is bad, because the plan was built on a number that was never real. The hardware is often fine. The assumption was wrong. That is a fixable problem. Fix it before the outage, not during it. If you are wondering whether this applies to your situation because you are in the south, or because you have a newer panel, or because your installer showed you different numbers, test it. That is the entire methodology of this series. Do not take my December number as a universal truth. My latitude is not your latitude. My shading is not your shading. My panel age is not your panel age. Take the method. Run your own 30-day log in the worst month for your location. Compare to your spec sheet. Find your own real number. That number is the foundation your plan is built on. If you have solar installed, here is your assignment. Run it for 1 week. Log your actual daily output, total watt-hours produced, not peak wattage. December numbers, not June numbers. Drop them in the comments with your approximate latitude, your panel age, and whether your installation has any shading between 9 in the morning and 3 in the afternoon. We are building a community data set. Real numbers from real roofs at real latitudes. I will compile the results and post them. The spec sheet says X. Let us find out what reality says across a few hundred installations. The data is more useful than any single test, including mine. Next episode, Layer 3. Thermal regulation. Your gas furnace does not work without electricity. Your wood stove works without electricity, but has a 2-hour startup time in a cold house and a smoke output that will flag your chimney to anyone within half a mile. Your electric space heater draws 1,500 watts, which is your entire power station capacity in 1 hour. Heat is the most dangerous failure mode in a winter outage, and it is the one most people have the fewest backups for. We will test 3 heating systems, calculate their real BTU output at -10 Celsius, and build the decision tree for which one you actually need. The numbers are not what the packaging says, they never are.